answer is 4 times 10 to the negative 8 molar. So, you know, please be able to calculate pH, or if I give you, if I give you the hydrogen ion concentration, be able to calculate pH, or if I give you pH, be able to calculate the hydrogen ion concentration. Yes?
Question. Do you look up a 1.4 unit?
I did. Yes. Please know your units. Do not ignore units. Units are important. It makes a difference.
What was the answer?
It was 4 times 10 to the negative 8 molar.
Wait, which one you 4 times 10 to the negative 8? 3A?
3A
Is 4 times 10?
to the negative 8 molar. That's 10 to the negative 7.4. You know, and you should be able to have a general, usually I take up half a point for units. I always assign it points, like, if something is millimolar and you put volts, that's just not, please, unit, just pay attention to the units.
Sorry,
It's also important, because sometimes, you have to be aware that you're given a measurement in volts, but you need to convert it to millivolts or vice versa, those are important.
I'm a little confused. So 10 to the 7.4, correct?
10 to the negative 7.4.
Okay.
Remember, the pH is the negative log of the hydrogen ion concentration. So if the pH is 7.4, it's obviously the answer is going to be somewhere between 10 to the negative 7 and 10 to the negative 8. If the pH is 5.2, the answer is going to be somewhere between 10 to the negative 8 and 10 to the negative 6. So you should also check your answer, using your logic. The metazole group of histidine has a pKa of approximately 6.9. Calculate the ratio of unprotonated to protonated imidazole at normal serum pH versus the pH of 6.7, which is profound acidosis. So 6.7 means you are probably going to die. That's what that pH means. Show your work. Okay. So just remember that who've had algebra. This is directly related to the fact that if you take the log of both sides, negative log is Ka of the Ka is the pKa. The negative log of the hydrogen ion concentration is the pH. So if you subtract log from this side and put it on that side, and subtract log Ka from this side and put it on that side, then you have the following equation. You can always just, if you can't remember it.
Sorry, could you all go light? It's a little hard for me to see.
Can't remember it. You can work it out. But, okay. So, at a pH of 6.7, so and 10 to the negative 0.2 is so at pH 6.7, the ratio of ionized to unionized acid is 0.63. Okay, so more of the acid is unionized at pH 6.7. So at pH 7.4, do you think that ratio is going to go up or down? Just from logic alone, you're going to, as the pH goes up, what happens to the hydrogen ion concentration? It goes down. So do you think that's going to make this number higher or lower? So are we going to have more or less protonated acid as the pH goes up and the hydrogen ion goes down? Less, right? So this number is going to be smaller relative to this number. It's going to go up. So at 7.4, its math is exactly the same. It's going to be 7.4 is equal to 6.7, 6.9. And then this is going to be 0.5 is equal to the log. And so that this ratio is going to be the log of, sorry, this is 10 to the negative. Is 10 to the positive 0.5. What is that? What was it?
It was 0.3, no, it was 316.
Yeah, roughly 3.2.
So if I said, you marked it wrong for that. You gave me 2 out of 4. I don't know what happened. Look, this is the proof here.
Show me afterwards. There were 2 points for each of these. So most people miss points because they did one but not the other.
So there's 2 answers for this.
Yes.
Oh.
One at pH 7.4
And then the other one is at 6.7.
and the other one's at 6.7.
Okay.
And so what I'm pointing out here
Oh, you're supposed to know.
is what a big change in ratio this is,
Oh.
okay? At pH 7.4, 3 to 1, unprotonated to protonated. So only 25% is protonated. At pH 6.7, the hydrogen ion concentration has really not changed very much, right? But we now have more protonated than unprotonated.
So you
Only 2 out of 3 are protonated instead of 3 out of 4.
So you wanted that ratio
Yes, sorry,
Okay.
2 out of 5.
for the one that's
Yeah.
protonated
And unprotonated,
Oh,
right?
okay.
So-
What did you say it was again? The first ratio or the ratio?
The ratio for pH of 6.7 was 0.63, which means that only, 2 out of every 5 molecules are unprotonated. For 7.4, the ratio is 3.2, so 3 out of every 4 are protonated.
So do we wanna, is the higher number better or the lower number better?
Well, which is normal? 7.4 or 6.7? 7.4 is you right now. This is someone who is probably gonna die.
And the 3.2 is better.
It's, yes, it's most definitely better. Predict the effect of severe acidosis on hemoglobin state. It favors the T state, because the imidazole is more likely to be protonated. And therefore, it promotes the formation of a salt bridge. Yes?
I have a question, Phil. I read 1.5, and my reasoning was acidosis will decrease the pH, meaning more H plus concentration, thus favoring the T state.
Yeah, so, I already told you that it's acidosis, of course. It decreases the pH, right? We know that, that's given. So the answer is favors the T state because imidazole is more likely to be protonated, that's another point, promoting the formation of a salt bridge.
Okay.
Yeah, in a million years.
Okay, so those are the 3 things.
So the salt bridges are formed within the T state, right?
Yes, so hemoglobin in the T state, the subunits at the juncture between the salt subunits, we have the salt bridges that stabilize the T state. And one of those salt bridges involves the positively charged imidazole and the aspartate.
So more or less, you've kind of drawn everything we've gone over. Are you gonna, and you don't have to say exactly what it is, but are you gonna have us draw something that we've already seen or drawn before on the final?
Draw something?
Yeah.
I mean, I didn't ask you to draw anything yet. On this exam.
I'm saying like because you've done, like, I think you've drawn almost everything, like we've drawn amino acids, we've drawn,
Oh, we're
nucleotides,
having
we've
draw
drawn
a structure,
mitochondria.
so jumping ahead, you mean, maybe.
But will it
Really,
be
the only
okay.
structures that we have asked you to make sure are amino acids,
Phospholipids.
The
phospholipids,
phospholipids.
and nucleotides. Right, and I haven't asked you to memorize the side chains or the nitrogenous base, just the, basic structure of nucleotide, basic structure of amino acid, basic structure of phospholipid.
So what I'm asking is, will you have us draw something that we have drawn before? Or will
I
it
could.
be on the final?
I won't ask you to draw anything besides those, and since I've asked you all 3 of those, then. yeah,
That's what I'm at, yeah.
Yes, then it'll be limited to those 3 things, in
Okay.
terms of chemical structures. Right, so, yeah. That was jumping ahead, but any more questions? Okay. Davies et al. Is in the paper from 2021, report on the case of a patient arriving with an arterial pH of 6.7. Do you expect the fractionate of oxygenated hemoglobin to be higher or lower than normal? Will you briefly explain the reasoning with regard to T and R state? This is very similar to the last question, but it's also, you don't need to have answered the last question to get this, because we said, remember, that acidic pHs favor the T state. That was just something we went over. So acidic pHs favor the T state, and they favor the release of oxygen, a low affinity state for oxygen. So you expect the fraction of oxygenated hemoglobin to be lower than normal.
Can you go over like the 3 checkpoints for this one?
Sure. T state is favored, low affinity for oxygen, therefore lower oxygenated hemoglobin.
Right.
So, any questions on 4, 5, or 6? I circled the correct answer for everyone.
What's the meaning for 5?
5, okay, yes. I mean, it's, that 5 is just a factual of all the secondary structures. Only the polypeptide or polyproline type 2 helices are not stabilized by hydrogen bonding along the backbone.
How is 4E false? True.
If you put two chemicals together and they react to
Mhm.
form a product, then you can say that that is a favorable reaction under the conditions that you just carried it out. That's just the definition of favorable.
Wait, so E is true?
Yes,
it's
E is true, right? If you have if you, like I said, if you put two chemicals together and they react, the reaction is favorable under those conditions.
So you can't have a reaction where they undergo if they're not favorable, right?
Under the and it's not favorable under those conditions, no.
Sure.
You can have a reaction that is unfavorable under standard conditions, that becomes favorable under other conditions.
Sure.
The diagram is below is guanine, and I just wanted you to draw guanine monophosphate. And what I'm looking for,
This is why I asked the question about where the fifth carbon was,
right,
cause I was confused at, like, yeah, but it's that.
blah, blah, blah. Okay, this is the 1' carbon. This is the 2' carbon. I did not say it was guanosine deoxy monophosphate, so therefore it has a hydroxyl group on the 2'. This is the one that would be missing in DNA. This is the 3'. This is the one that's always there, and where the new nucleotide is added during DNA synthesis. This is the 4', 5', monophosphate. Okay. You should just know the structure of a nucleotide generally, and you should definitely know where the next phosphate is gonna be added. If I did ask you to draw a dinucleotide, imagine this was DNA. If I asked you to draw a dinucleotide, this would be the phosphodiester bond. I should have it on that side, but I'm running out of room here. Okay,
Sorry, why did you put the OH? I'm kinda confused. Is that the 3' there for the next location?
yeah.
Professor, you fast.
Yeah,
I didn't get to write it down.
Well, luckily some,
We need that.
Just to make a note to yourself right there to go look up the structure of the two nucleotides joined together.
So was it just that one drawn again at the bottom?
Yeah,
Okay.
yeah, I mean, you just add
Without, yeah.
the phosphorus here.
So you-
then
and then you
another-
draw that again.
And then another nucleotide, right?
So you add a phosphate to that, the 3'.
Right, that's how DNA is synthesized, right? The phosphate comes in here, kicks out water, so the hydroxyl group is kicked out. And then you have the phosphodiester bond here.
Okay.
That was a dinucleotide, right, you said?
What?
Dinucleotide was what
Yeah,
you drew?
a
there?
dinucleotide, right. remember that a dipeptide? This is the peptide bond. And at physiological pH, the amine is protonated and the carboxyl group is unprotonated. Would you find guanosine monophosphate in DNA or RNA? It's found in RNA because it is not deoxy guanosine monophosphate. Briefly define oxidation or reduction. I think almost everyone got this right, if not everyone. Loss of electrons is oxidation. Electrons, we can do that. Skipping 10 and 11 unless you have questions. Yes.
And you're getting please.
10, trypsin cuts between lysine, after lysine or arginine.
How are you supposed to do
I tell you that.
My fault.
Okay,
It's the
okay.
key, right?
No,
So I do say the R1 residue, so that you do have to understand what I mean.
Oh.
So,
I put D.
What was the answer? I didn't have.
It was
I don't have
C.
it.
it's C because it cuts after, the R1 is the side chain that it cuts after. So there will be the active site, it'll cut between two residues, right? So the active site accommodates the R1 residue, that's typically typically but not always the residue that confers specificity, and the residue that it cuts after.
Oh, so it's,
Does
so
R1
it's
mean?
after, it cuts
Yes,
after
it cuts
residue.
after arginine. There are,
So-
yes, it cuts the peptide bond immediately after that. Although there are some enzymes that cut it before.
How would we know if it cuts before, like on the exam? What would you say?
I'm not gonna put it on the final, so
Alright.
Okay.
I did not include that on the study guide.
If you said the R2 residue, would it be A?
No, in case of trypsin, trypsin will cut, the R2 residue is unimportant unless it's proline, in which case trypsin will cut.
Sir, I'm still confused. So when you say R1 residue, do you mean after like the R? And
R is side chain, and the
Oh.
active site, the side chain enters the active site, and it will cut the peptide bond in between lysine or arginine, and then any side chain except for proline. It will cut in between lysine or arginine, and then any other amino acid except proline. But it's not gonna be on the final, remember, it's not on the study guide, so.
Yeah, but.
Okay, just so you know, yeah.
It's still good to know. So it just cuts
I'm not-
just after the arginine basically.
I didn't say that.
Yes, it just cuts after arginine or
Wait,
lysine.
So we only care about the study guide?
You're planning on taking the MCAT, so you should care about everything. But yes, that's typical for proteases, they will cut after specific amino acids typically, though occasionally they will cut before specific amino acids.
Okay.
Any more questions? Okay, 12. The delta G naught, the delta, the free energy under standard conditions for the isomerization of glyceraldehyde 3-phosphate to dihydroxyacetone phosphate, which is where are these two molecules found? This is an isomerization, right? In glycolysis, thank you, yes.
Wait, so
So,
even though this is a summarization, these are not isomers?
they are
I had a
isomers.
question that.
They're not stereoisomers, but they are isomers. They're structural isomers. So this is actually a reaction that takes place in glycolysis. When fructose 1,6-bisphosphate is cleaved, it releases one molecule of glyceraldehyde 3-phosphate and one molecule of dihydroxyacetone phosphate, but it is glyceraldehyde 3-phosphate that is the substrate for the next reaction. So, the under standard conditions, or you can write this, if you take the natural log of both sides, you can write, or people usually do this, right? So, those are both the same equation, right? Algebra. So the equilibrium constants, if you throw in all the numbers, this is e to the negative 7.5 kilojoules per mole. This is why units are important, because this is in kilojoules, but R is often given in joules. So you have to remember to convert that to 0.008314 kilojoules per mole degree C. No, yeah. Times the temperature, which is,
Standard, right?
what did I say it was? Oh yeah, I said in the exam that it was the standard temperature in this case. So it was 290, right? And then if you do all the math here, you get e to the negative 7.5 over 2.47 is equal to 0.05. So that's the equilibrium constant. Is that favorable or unfavorable?
It's favorable.
So first of all, delta G naught is positive or negative?
It's almost positive, it's unfavorable.
Right. So what this says, remember, what is an equilibrium constant? Under standard state, which actually, in this case, you know, we only have one product and one reactant, right? In this case, it's the concentration of if this is 0.05, do we have most of our molecules as dihydroxyacetone phosphate or as glyceraldehyde 3-phosphate? They're almost all in this form. 19 out of 20 of them are dihydroxyacetone phosphate. In the cell, the cell draws off glyceraldehyde phosphate during glycolysis, maintaining a ratio of 1 to 100. If the ratio is 1 to 100, which direction does this go in order to restore equilibrium? It's gonna go to the left, right? It wants to get back to 5/100. So it's going to favor the production of glyceraldehyde. If the cell maintains this concentration, it's the bulk of this reaction is, such as it is, isomerization is going to favor the production of more glyceraldehyde, right? Phosphate. You disturb the equilibrium such that, in fact, glyceraldehyde 3-phosphate levels are low compared with equilibrium. At equilibrium, they should be this, that's 1 out of 20. But the cell keeps it here. And so isomerization is more likely to go in this direction.
Wait, so, the cell, in a normal cell is 1/200.
That is how it is maintained during glycolysis.
But in this example, it's 1/20.
That is what it is at equilibrium under steady state conditions.
At equilibrium is 1/20.
At equilibrium, the ratio of glyceraldehyde phosphate to dehydroxyacetone phosphate is 1 molecule of glyceraldehyde phosphate to 19 molecules of dihydroxyacetone phosphate, 1 out of 20.
Okay, so being 1/100 pushes more gap to be made so that it can be what it could be.
Right, so now there's excess dihydroxyacetone phosphate, and dihydroxyacetone phosphate is more likely statistically to isomerize to glyceraldehyde phosphate and vice versa. So, in other words, now this reaction becomes the more common reaction. It pushes it in this direction to restore the equilibrium conditions, which is Le Chatelier. So now, I just asked you to calculate delta G for this situation. Delta G for this situation is where product is reaction is. So then we have oh, did I miss a negative here?
No.
No.
I did the exact same thing, but you marked me wrong, please. You did, you crossed out the .001, you did 100.
You're right. You're correct.
Low key.
Oh, you know what? I miswrote the delta 12, the question, right? I said the isomerization of GAP to dihydroxyacetone is 7.5. Should be the other way around. So,
Oh, snap, that's what the question you
I said, oh, well, I wrote it the wrong way around, so I need to calculate it as if it was the other way around. But I grant you that is confusing.
Yeah, so you're gonna give everybody extra.
Well, you know, only if you can show me that you answered what would have been pertinent. Okay, well, come on.
I did.
Okay, so then this is,
So it's 1/100.
It's -3.9.
negative 3.9
Yeah.
times 2.5?
Yeah.
The total, the whole thing.
The whole thing.
Oh, the whole thing in
Yeah,
total.
so,
Oh, okay. Okay.
over most.
Okay, so it, yes, yeah, I had misstated the question.
That's 3.9.
Yeah,
You get
3.9.
247.
What?
247.
Oh, no, that's a point right there, 2.47. R expressed
Great.
in kilojoules instead of joules.
If you ask this for the final, you're gonna specify.
Yeah. I won't give you this exact question.
The reaction for this
I might give you
is
something similar.
unfavorable or is favorable.
During glycolysis, because the product because the product is kept relatively low, below the equilibrium value, the delta G is favorable. Okay.
I have a question.
Oh, wrong one. Okay,
You gotta move it or not move it to the.
oh, we're doing okay. We're doing okay, we only have a short amount left. Well, no, okay, we have half the exam left to go. Yeah.
Shouldn't that read like 7.5 plus the R, which is 8.314 times
So-
10 to the third kilojoule?
So I just converted it to,
So R and T-
8.314 times 10 to the negative third
Mhm.
kilojoules per mole. Keep everything in kilojoules. No, Gotta that's why you have to pay attention to your units. And make sure that everything is consistent. And that, this is true in medicine too, people switch back and forth between all kinds of different units, and you have to make sure that you're being consistent. 13 and 14, any questions about those? Most correct answer, P50 is equal to the value of the partial pressure of oxygen when half of the myoglobin is bound to oxygen. What is the question about that? That's the, yeah,
I think it's
that's just the definition.
Correct, I'm just like, are they all correct, and this is like, not?
So a lot of people were confused about myoglobin versus hemoglobin. Myoglobin is the one that does not have a sigmoidal shape to its curve. So A is wrong. The value of Km can be calculated at half Vmax is totally irrelevant to this question. It's just like something to do with enzymes that I threw in there. The cooperativity index can be calculated from the ratio of, again, I was just making up things. The curve declines exponentially and approaches zero. It increases exponentially and approaches the 100% saturation. So, as the partial pressure increases, so that's just the opposite. Any other questions? No? Okay. 15. Amino acids that were absolutely conserved were 36 and 51. Thank you for pointing that out. The amino acids that are shaded have a common property, and that common property is that they are almost all non-polar hydrophobic, right? And that means that those are important, those are structurally important, and they are in the hydrophobic core protein.
Yeah, there's no new question.
Briefly define domain, it's a contiguous or continuous stretch of amino acids and polypeptide that fold independently of the rest of the protein. That's the definition, yes.
For B, how would you know that it's non-polar hydrophobic?
Well, because I gave you, the one letter amino acid abbreviations at the end, and I expected you to know which amino acid side chains were polar or non-polar. So, you know, it's like, tryptophan, tyrosine, leucine, phenylalanine, valine, isoleucine. Those should all immediately jump out at you as being non-polar. Isoleucine, valine, leucine are all aliphatic, phenylalanine, tyrosine, tryptophan are all aromatic. Come up to me afterwards and, yes. C, where do you expect to find the shaded amino acids? Typically, hydrophobic, non-polar amino acids will be in the core, the hydrophobic core. So that's the central region of a fold, of a domain, a fold, where the amino acid side chains are buried away from water. So that is one of the forces that promote protein folding, is the burial of hydrophobic residues, side chains. So, just like oil, they don't like to be in contact with water. Or water doesn't like that. So, it's one of the several main, forces that promote protein folding, is the burial of hydrophobic side chains. 16. The first one is dihydroxyacetone, and the second one is glyceraldehyde. And they are isomers, but they are not stereoisomers, they are structural isomers. Yes?
Did you go for D for 15?
Yes, but I'll go over it again. A domain is a continuous stretch of amino acids in a polypeptide, that was one point, that folds independently of the rest of the protein. 2 points. 16 are, they're structural isomers, not stereoisomers. Glyceraldehyde is an aldehyde, the carbonyl is on the end of the molecule. Dihydroxyacetone is on the carbonyl and carbon. Yeah.
But I don't think it is, cause.
I don't think it is, cause it would be.
Yeah, but it's freaking. Never mind.
So 17, the oxygen binding curves of myoglobin and hemoglobin. The y-axis is the oxygen saturation of each globin. On the graph, the non-sigmoidal curve is the myoglobin, which indicates a lack of cooperativity. So this is the hemoglobin, and this is the myoglobin. Approximate P50 for myoglobin and hemoglobin based on the graph, and briefly define P50. P50 is the partial pressure of oxygen where the globin is half saturated. So if you just draw a line over from the 50% value, myoglobin was at around 7 millimolar mercury, millimeter mercury, and hemoglobin was around 27 millimeter mercury.
Sorry, what is the full answer?
The definition is P50 is the oxygen pressure, partial pressure, where the globin is half saturated with oxygen.
You
So-
want us to define it?
Yeah, so that was the definition part. And then the part where you find the, P50, you take the 50% value and you just go over and look what the partial pressure is. On the graph, predict the effect of acidosis, decrease serum pH on the oxygen saturation of hemoglobin, and it decreases the oxygen saturation. That's acidosis, yeah. Acidity decreases the affinity for oxygen. And promotes the T state, promotes the protonation of the histidine, and promotes sulfages.
So the dashed line is what acidosis is?
Yeah.
Okay.
I wasn't very picky, just a line teacher. Briefly discuss the reasons hemoglobin shows cooperative, indicate the general region where 2,3-bisphosphoglycerol glycerate is bound to hemoglobin, and that is in the T state. So in this general region, what?
At the tissues?
When it's in the T state, when it's in the low affinity oxygen state. And that helps stabilize the T state and prevents it from moving back into the R state. Hemoglobin shows cooperativity. Sort of, first of all, myoglobin is a monomer, so it does not have the capacity to show cooperativity. Whereas hemoglobin has 4 units, and the 4 units, the 4 subunits, shift structure coordinately. So that's what I was looking for. 18, any questions about 18?
So like, it, cooperativity has nothing to do with the iron in it.
Not directly.
We said, hemoglobin has 4 subunits that shift structure coordinately.
Yeah, myoglobin is just a single.
It's just a
It's just a single unit, yeah, it doesn't form a complex.
So catalysts work in the forward and the reverse?
Yeah, they can catalyze either the forward or the reverse, typically, because they're just reducing the activation rate.
Wait, in a catalyst, enzyme catalyzed reaction ratio of products to reaction will change?
That's correct, right? Does not change the equilibrium.
Wait, it doesn't say anything about equilibrium, it just says in an enzyme catalyzed reaction, the ratio of products to reactant changes.
What is the ratio of products to reaction called? The equilibrium. So, right. Okay, so in the last question, we have us a Lineweaver-Burke plot. We'd say, very likely to be on the exam. Okay, here is our Lineweaver-Burke. And we have okay, so the first thing was label the axes. I wanted to make sure that you knew in the Lineweaver-Burke plot that you're plotting 1 over velocity and 1 over substrate concentration. And that's the difference between a a line weaver Burke and a sort of more conventional plotting. The fact that you have plotted the inverse of the velocity and the inverse of the substrate concentration makes it a little counterintuitive, because this is the enzyme and this is the enzyme plus inhibitor. Right, you would not be, if the velocity goes up more quick, if the velocity is reduced with the inhibitor, 1/, the velocity is gonna go up with the inhibitor. So you have to keep that in mind.
Wait, what was it again? I'm sorry.
So this line here is the enzyme with the inhibitor, and this line here is the enzyme alone. If you expect the inhibitor to reduce the velocity, it does, it reduces the velocity, but of course, it increases 1/, velocity. If velocity is reduced, then 1/, velocity is increased. So a number of people got those two confused.
Yeah.
As you remember, in Lineweaver Burke, they are the opposite of what you would expect in a conventional plot. I put in the numbers so that they worked out roughly, this one, oh, no, this was around -0.5, and this was around -0.2. And this was around 0.5, and this was around 0.3. So, for the enzyme alone, 1/v max was approximately 0.3. So V max was approximately 3.3 millimoles per liter per liter minute. Whereas with the inhibitor, Vmax was about 2.
So basically, if you didn't know which one was the enzyme or the inhibitor, you got everything.
Subsequently wrong.
Yeah.
Although I think I gave people partial
Yeah,
credit,
you did.
for doing the calculations correctly.
Okay.
Okay, so that was the answer for that. Again, I gave partial credit for doing the calculations correctly, even if you got them confused. For Km, for the Michaelis-Menten constant, 1/Km was approximately 0.2. So Km approximately 5 millimolar. Whereas this Km was approximately 2. So these are the intercepts.
Is that for D?
That's what D, I think.
That was D.
Cause I did 2, I didn't get credit.
Oh, okay, well, show me.
Wait, where did you get?
So, this is 1/Km here, the intercept, and this is, intercept is 1/Vmax. That's the utility of a Lineweaver Burke. You can get the value of Vmax and Km just by finding the intercepts, the X and Y intercepts.
So, for this one, we just had to look at the graph, right? There was no.
Yeah. Yeah, just have to look at the graph and estimate where the intercept was. I have to say in E, I gave you full credit for E, for saying, because I forgot to give you the enzyme concentration. my bad, but, I was looking for this. Bmax is equal to Kcat times the total amount of enzyme, so Kcat so as long as you wrote either of those equations, I gave you a point. Questions?
Did you have to write that opinion out, or could you just like show like division?
You just have to write one or the other of those equations out. So showing that you knew how to calculate Kcat from Bmax.
And that was out of 2 points, right?
That was 1 point, I just gave you 1 point for that. Were you successful in designing an inhibitor that binds to the active site of your doom scrolling enzyme? The answer is not entirely. A competitive inhibitor should change the Michaelis-Menten constant, but it should not change Vmax. Remember, a competitive inhibitor, if you continue to add substrate, you will eventually outcompete the inhibitor and reach the same maximum velocity. And this is a mixed inhibitor because it changed both the maximum velocity and the Michaelis-Menten constant.
Wait, sorry, was the total, enzyme not 5-NN?
No, that's not it, that's the, inhibitor.
But that's not the total, oh, okay,
No, that's the inhibitor.
So what's the final answer?
For E?
For F.
Oh, for enzyme, for F, there were 3 points. Were you successful? 1, not entirely, or no. Point number 2, a competitive inhibitor should change the Michaelis-Menten constant, but not the maximum velocity. 3, so this is a mixed inhibitor. So, any questions on any of that? So this exam does cover some topics that are not gonna be on the final. What? The what?
What we just talked about, that's what we're going
Yeah, the enzyme kinetics is on the final. Just memorize this.
Oh, okay.
And also the conventional way of drawing a diagram, right? The conventional way it's not a concentration. Okay, conventional way is just to plot substrate concentration versus velocity. And for a particular concentration of enzyme, remember this is a particular concentration of enzyme, as the substrate increases, the velocity will increase until it reaches the maximum velocity for that particular concentration of enzyme, meaning you've saturated the enzyme sites. Okay. So what is the maximum velocity here? It's that line that you're approaching. What? Right, and Km is gonna be halfway there, I believe. So,
That's what we need to know for 8.
yeah, I mean, you should know what these terms mean, obviously. Yes, I could either give you this, or the Lineweaver-Burke, and ask you what is Km, what is the maximum velocity, and then if I do give you the enzyme concentration, you should be able to calculate Kcat from that, right?
That's what we're
Yeah, and, yeah, if I give you the total amount that's on hand. And you should, you should know the difference between a direct inhibitor and indirect inhibitor. Direct inhibitor, binds to the active site. We have talked about, so for example, name of direct inhibitor we just talked about. That was on the fifth quiz. Lipitor. Lipitor is structurally, part of the Lipitor is structurally extremely similar to HMG, and that binds into the active site of HMG-CoA reductase, and therefore it should behave like a direct inhibitor, as opposed to an allosteric inhibitor. We've talked about a number of allosteric inhibitors, especially when we're talking about feedback inhibition. So, hopefully she left all her stuff here, so she's coming back. We're gonna go over the second exam, I don't wanna drive anyone to despair. We only got 15 minutes left, okay, let's go, second exam. Hopefully this is all coming back to you guys, right? Yeah. And so are you. Okay.
The Celine Dion song? It's coming to me.
I don't know that one. I also know the Titanic one. I even saw it in concert once.
Is that your concert?
Yeah.
But you don't know the song is coming back to me.
No.
Just imagine him.
Seems so long ago, honestly. Before I had children, so it's like a whole nother lifetime. Ion channels. Oh, any questions about one or two?
Can you go to two?
Two, okay. What do we know about the sodium potassium pump? Well, okay, in case you don't remember, sodium is pushed out against its concentration gradient, and potassium is pushed in against its concentration gradient, and this is all powered by the hydrolysis of ATP. So the A, the energy required to move potassium into the cell is supplied by the movement of sodium into the cell. So that's not right. Again, down its concentration gradient. One thing you should know is that sodium is concentrated outside the cell and potassium inside the cell. So moving sodium down its concentration, it will all be out of the cell. Energy required to move B, the energy required to move potassium out of the cell. Again, that does not require any energy, you just have to open a potassium ion channel and it's gonna flow out. C is correct. D, the energy required to move potassium out of the cell, once again, doesn't require any energy. That's its natural, the direction it will naturally flow. E, the energy required to move potassium into the cell is applied by the movement of sodium out of the cell down its concentration gradient. Again, sodium will move into the cell down its concentration gradient. Okay. Also, E supposes that potassium and sodium are both that's an antiport, but you also should know what the difference between an antiport and a symport is, but actually it wasn't necessary to answer this question.
I mean, it kind of helped.
It helped though, yeah. You can rule out answers that way. So ion channels exhibit ion selectivity, meaning, and all I was looking for is that channels will pass a particular ion through the membrane, but not others. simple.
Number 4, please.
Yes. Assuming the pH of the mitochondrial matrix is 7.8. Here's our mitochondria, minus all those, membrane invaginations. Which has the higher concentration of protons? 6.8. The potential across the inner membrane is 168 millivolts with the matrix being negative. Calculate the free energy required to transport a mole of protons across the inner membrane at 37 degrees. Okay, so for this one, you did require that
So you're not gonna at least have no formulas on the exam, you have to memorize everything that you can understand.
yeah,
Oh, no, I was just asking, okay. Just in case.
you've already memorized it once, right?
Yeah.
So just refresh your memory. There's so many of them are related, right? Delta G is equal to R2 log something. Right?
Right, for the next equation, it's out versus in, and then for this one, it's in versus out.
This one does not suppose a directionality.
Well, I'm not in the slide, it says in.
For the next equation, we are specifically calling,
It's gonna be left to right.
right, we are specifically designating an out and in. And this equation, it's just between two spaces wherever they may be. They could be in a beaker separated by a membrane.
So then how do you know which one's the C2 and which one's the C1?
Well, there's two ways. I mean, typically, this is the, when you're talking about an equivalent,
Well, this,
constant, we're talking about products versus reactants, so it's where you're moving from to.
So the C2 is where you're going to and C1 is where you're starting from, right?
Yeah, if you consider it if you consider it as a reaction, you're moving protons, right? The other way to do it is the way that I did it actually when I was doing this question, which is, if you're moving a mole of protons from the matrix, actually I didn't specify, so I would have accepted it in either direction, as long as you were consistent about it.
I do have a question regarding this.
Right.
Like, I got 1 point deducted because you said the signs need to be the same for the both concentrations, which I
That
don't
is-
understand why.
Okay, so, which way? If you're moving the protons into the intermembrane space, is that gonna be against the concentration gradient or with the concentration gradient?
With the
Moving it-
concentration rate,
If you're moving it into the intermembrane space,
it'll be against.
so is that delta G gonna be positive or negative?
Negative. I mean positive, it'll be positive.
Okay. If you're moving it into the intermembrane space, are you moving it against the potential or with the potential?
With the,
Are you moving positive ions into a positive space or into a negative space? Is it gonna be favorable or unfavorable?
so negative space would be favorable.
Right, but is the intermembrane space negative or positive?
It's more negative. No, it's
The intermembrane space is
more positive.
very positive. So is that gonna be favorable or unfavorable?
Unfavorable.
Right, so that's what I mean. It has to be either all, if you go the other way, This is the way of the proton motive force. The direction of the proton motive force. Proton motive force moves hydrogen ions, protons down their concentration gradient, therefore it's favorable. And it also moves it from a positive space to a negative space, therefore it's favorable.
Okay, that makes sense, but doing the math, I got the negative.
So if you do the math and you have one positive number and one negative number, then you've done the math wrong. You can just say that by default, right? Okay, so I chose to move it into the intramembrane space, but if you were thinking about it being moved into the matrix, then it would just be the opposite. Okay, so this is going to be equal to R, which is 8.314 joules mole per mole times 310 times the log of
The H concentration.
yeah, negative 6.8 over negative, the 10 to the negative 6.8 over 10 to the negative 7.8 plus Z times Faraday's constant, which is 96.5 kilojoules per mole volt. So Z is 1. This Faraday's constant is 96.5 kilojoules, so gotta remember that that's in a different moles volt. So now you have to convert to volt to get this correct. It's not it's 0.168 volts.
Oh, cause it's in units.
Yeah. So if we convert this to kilojoules, we now have something around 2.5-ish, approximately 2.5 kilojoules per mole CK, rather. Oh no, got K's out. Natural log of 10. The natural log of 10 is 2.3. That's the conversion between natural log and log. So this is 2.3.
Yeah, because I did the other way around and I got negative 2.3.
Right, so then you would have to reverse this and make it a negative
Oh, I see.
0.168. And then this is 16.2 kilojoules per mole, and this is 5.93 kilojoules per mole, and altogether it's roughly 22 kilojoules per mole. But whichever way you're moving, if you calculated it such that you were moving the protons into the matrix, it would be exactly the same calculation but negative. Yes.
How do you convert the kilojoules over mole volt to volt? How you did with the 96.5?
So this is 96.9 kilojoule moles volts times, you can barely see it there, 0.168 volts. That's the membrane potential.
How did you get, the 2.3?
That's the natural log of 10.
Sorry, what was the 6 part? This is my
This is the natural log of 10. The log of negative 6.8 over 10 to the negative 6.8, which is the hydrogen ion concentration.
So you divide those two, right? Or
Yes.
you could just subtract it from,
It's 10 to the 1,
yeah.
which is 10. Right. And 2.3 is the natural log of 10. You don't need to remember that. You calculate it or something, but.
No, I'm just telling you that.
Right.
I Right, when I put it on, I thought that I got something very good.
What's the final answer?
It's like
From 22, it's approximately 22.1 kilojoules per mole. And that's positive 22.1 kilojoules per mole if you're moving it into the intermembrane space. If it's moving from the intermembrane space into the matrix, then it's negative 22. Yes.
For, in my instance, where I did the other way around, which one am I doing, the negative on?
So
Am I doing
you
the
should have
chart?
had, if you have defined, if you're moving it in the opposite direction, and
Which unit am I,
you should have had
is it the negative 0.1?
a negative 0.168, right, because the inside is negative. Question, yes,
So the Z has no value?
Z is 1,
Is it charge?
because it's charge, Z is charge. So in this case, the charge is 1, plus 1. Because it's a proton, so it's just got a positive 1 charge. If it was calcium, we'd have to make it plus 2. Chloride, we'd have to make it negative 1. Okay. Okay. Hexokinase is an enzyme that phosphorylates glucose when it enters the cell. Any questions? An individual suffering from hyperkalemia with a serum potassium level of 7.7 millimolar and a normal cellular potassium level of 140 millimolar. So just to note, hyperkalemia is when the serum potassium levels are above the normal serum potassium levels, and hypokalemia is when the serum potassium levels are below the normal serum potassium levels. So in both cases, we're talking about the serum potassium levels. The cellular potassium levels don't typically change. And same with hyper and hyponatremia. Hyper is relative to normal sodium levels, and hyponatremia is low relative to normal sodium levels in the serum. Calculate the reversal potential for potassium under these conditions. So, we went over something similar. Did we go over this? We went over this like right after the exam, didn't we? Because everyone wanted to know the answer. So the answer again was, 7/140 equal to negative 80.7 millivolts. The resting membrane, so normally what is the resting membrane potential? Negative 90, or even high, lower, between negative 90 and negative 95, even close to negative 100. This is a normal. So now the resting potential has gone, the resting potential is set close, but not normally quite at the potassium reversal potential, though sometimes it does get down to the potassium reversal potential. So if the potassium reversal potential goes up, the resting membrane potential also goes up. And that is a disaster for many excitable membranes. It means that they're hyper-excitable. It's much easier to excite them. It's much easier to get to the threshold potential. Just to note that the reversal potential for sodium has no bearing on the resting membrane potential. So if we change the reversal potential for sodium, that won't really change anything. Okay. Actually, while we're doing that, so a normal resting potential for your typical excitable cell is gonna be around -70, maybe a little less. So that's gonna be the normal resting potential. The normal threshold, -40 to -50 millivolts is the threshold for generating an action potential. So typically what's gonna happen is you'll get a depolarization due to ligand-gated ion channels. You know, your typical glutamate receptor or acetylcholine receptor in the membrane opens up, sodium flows in, it may or may not get to the threshold potential. If it does get to the threshold potential, that will trigger the opening of which ones though? Because ligand-gated channels are often sodium channels. Well, which kind?
Oh, the ion
These are ones that are responding to a depolarization, so they are called voltage-gated sodium channels. You get the voltage-gated sodium channels opening up. I don't know if you can see anything that I wrote on the board. Okay. Also known as NAV, sodium voltage-gated. They open and sodium flows into the cell. At some point later, they don't close, I mean they close, but they enter a state that's referred to as the inactivated state. And sodium stops flowing into the cell. Meanwhile, back at the ranch, the voltage-gated potassium channels have opened. And potassium starts flowing out. So as the potassium flows out, that repolarizes the cell. And the sodium is flowing in, so it becomes very positive. Now potassium is flowing out, and it becomes negative again. And it usually overshoots the resting potential, referred to as hyperpolarization, and then eventually comes back up to its normal resting potential. Yes?
Hyperpolarization, is the potassium still coming out or?
Yeah, I mean, the potassium is flowing out. Right, but it repolarizes to the point where it goes down below the normal resting potential and it hits roughly the reversal potential of potassium. And then it starts to slowly rise again as what is causing it to return to its normal resting membrane potential? The sodium-potassium pump. Sodium-potassium pumps busily, because there was all this sodium flowing into the cell and all this potassium flowing out of the cell. So the sodium-potassium is busy moving, shoving all the sodium back out and all the potassium back in and returning everything to its normal state. And this all happens in, like 1,000th of a second. Or maybe 5,000th of a second. Everyone's really tired now. Okay, how might the action potential be affected by hyperkalemia? Hyperkalemia, remember, is going to move the resting potential up, and so it's going to make it easier to generate an action potential. Yes, it will be overstimulatable. Yes.
Wouldn't that be the same thing as hypernatremia?
No. Hypernatremia is when you have excess sodium outside the cell. It doesn't affect the resting membrane potential. because the resting membrane potential is set by the reverse potential of potassium.
You said much easier to reach resting?
Oh, so, so remember that it's potassium leak currents. There are classes of potassium channels that are just always opening in the cell membrane, letting in potassium in excitable cells. And that pushes the resting membrane potential down for excitable cells till it's close to the reversal potential for potassium. So, but if the reversal potential of potassium rises from -90 to -80, the resting membrane potential is also gonna rise. So if the resting potential rises to here, instead of having to go from, -70 to -40 to generate an action potential, now you're gonna be going from like -60 to -40. So it's gonna be easier to generate an action potential. The cell will be hyper excitable. And but more difficult, it's never gonna go back down, it's not gonna achieve the correct membrane resting potential. So it's gonna be more difficult to repolarize. Does that answer your question? Got it? Okay. Okay, during glycolysis, when an enzyme catalyzes the reaction regarding the cell's commitment, that's the addition of the second phosphate to fructose. So that's phosphofructose kinase. Also, because this is the cell's commitment to glycolysis and it uses up an ATP, this enzyme is quite heavily regulated. Right? So final products of anaerobic fermentation in humans, lots of people got this wrong actually. It's lactate. Remember, humans do not leaven bread or produce beer. Okay. When and why anaerobic fermentation is necessary, it's when there's no oxygen present. And it's necessary to regenerate NAD+, so that you can go through glycolysis over and over again. Some reactions that occur during glycolysis have a positive free energy, such as reactions 4 through 6 below. This is under standard conditions. They have a positive free energy under standard conditions. Explain the mechanism used by cells to make these reactions favorable. So we really answered that question on the first exam. What was the mechanism? So reaction 4, for example, is the isomerization of dihydroxyacetone to glyceraldehyde, dihydroxyacetone phosphate to glyceraldehyde phosphate. And why is that favorable in itself?
The concentration, there's a small concentration of GAP, smaller than DHAP.
Right. So, and can you make that a general statement now? The smaller concentration of?
One of the products pushes the reaction forward.
Yes. If you keep a low concentration of products, that will compare to the equilibrium right? If you keep the ratio of products low compared to its equilibrium state, then that will push the reaction forward.
What were the 2 points?
Reactions draw off products, keep product concentration low. Either of those. And then that shifts the reaction in the favorable forward direction, or that makes the reaction favorable.
I think I wrote both of that.
Okay, well, come up to me afterwards, not right now.
Yeah.
We're over time already.
Yeah.
Okay, quickly, enzyme plays a role in glycolysis is phosphofructokinase, and then the other one is gluconeogenesis. AMP stimulates glycolysis, right? Lots of ATP floating around inhibits glycolysis, but AMP or ADP stimulate glycolysis, and therefore inhibit gluconeogenesis. You don't want to go around making glucose if you don't have that much energy around, right? ATP stimulates gluconeogenesis.
Which one is inhibited by AMP enzyme?
Inhibited by AMP is fructose 1,6-bisphosphatase.
Took off 1 point because I forgot to say bye.
No, I didn't know.
But so, wait,
Go.
Yeah,
fructose 1,6-bisphosphate is inhibited by AMP.
okay, I'll take a look.
It's inhibited by AMP?
Yes. And the second point for this was that high AMP stimulates glycolysis, because ultimately, it makes ATP from AMP. And therefore it needs, since these are coordinately regulated, it needs to inhibit gluconeogenesis. Glycogen is not a disaccharide. Okay, sucrose, that's a good disaccharide. Incorrect answer, D. 14. This was pyruvate going to acetyl-CoA and then going through the citric acid cycle. So this takes place in the mitochondrial matrix. The enzyme catalyzing first reaction was pyruvate dehydrogenase. The reactions between the citrate and citric acid cycle. Two molecules covalently linked together to produce citrate are acetyl-CoA or the acetyl group from acetyl-CoA and oxaloacetate. Feedback inhibition, there were just so many examples of feedback inhibition here, including acetyl-CoA and ADH inhibiting pyruvate dehydrogenase, succinyl-CoA and ADH inhibiting the production, the enzyme that catalyzes succinyl-CoA. So any of those were good? Reactions that generate carbon dioxide were isocitrate to alpha ketoglutarate and alpha ketoglutarate to succinyl-CoA. These are irreversible reactions. They are very favorable, they're irreversible, they produce carbon dioxide, and therefore they are most likely to be regulated. So
Say the second one again?
they are therefore likely to be regulated because they're irreversible reactions.
Which two generate CO2?
The reaction that generates alpha ketoglutarate from isocitrate and succinyl-CoA from alpha ketoglutarate.
Okay.
15, 16, any questions? Okay, 17, we went over 17 twice in lecture. We did, actually, we did. Cofactors, thymine and lipoic acid. So, if you're looking at it, this is one of your vitamins here and over here. Covalent catalysis, this was the addition of pyruvate, sorry, I'm starting to lose it. Pyruvate to the cofactor, that's a covalent, a temporary covalent linkage. Or the addition of the acetyl group to the sulfide of the lipoic acid. So either of those were covalent temporary covalent bonds formed with the enzyme, during the course of the reaction. Resonance stabilization is this one where you can see the resonance structures. That's the resonance stabilization. The enzyme that catalyzes this reaction, you should recognize this as pyruvate. So this is pyruvate dehydrogenase, E1. But I gave you, pyruvate dehydrogenase is fine. The cofactors, resonance stabilization. Okay. There are no examples of general acid or base here. That would be either donating a proton or accepting a proton.
So there was no examples of A, right?
Nope. Electrostatic catalysis, there were a number of examples of positive and negative anions being positioned close to one another. Covalent catalysis, we just just went over.
What number is that, two?
Covalent catalysis is when the substrate makes a temporary bond with the enzyme. So either the pyruvate with this thymine or the acetyl group with the sulfur group of the lipoic acid. And substrate positioning, so that is reaction 4, where the substrate that is being transferred to the lipoic acid is in the active site right next to the lipoic acid. I know, that's why I'm trying to get through them quickly. 2 molecules that donate 18, lots of people, it was A and C, okay? The proton motive force is the proton gradient, and also the mitochondrial membrane potential, the negative charge that is in the relatively negative charge inside the matrix versus the positive charge in the membrane space. Both of those drive protons across the inner membrane. 2 molecules donate electrons, half a point each, NADH, FADH2. NADH has the larger PO, either because it donates to complex 1, which is a proton pump, so that assists in pumping protons and creating the proton motive force. Or you can just say that it has a higher energy, it donates the electron has a higher energy, so it is used to pump more protons. 20. Vitamin C accumulates in mitochondria. You are studying the reduction of dehydroascorbate to ascorbate, and believe the reduction is either carried out by oxidation of NADH or by nitrate. You are wrong, by the way, but that's your model, so let's go with it. Delta G is equal to negative NF delta P, where P is the redox potential. So for NADH, for both of them, this is negative 2 times 96.5 kilojoules per mole. For NADH, the redox potentials are 0.06 minus negative 0.32. And this ends up giving you a negative number. So that's possible. I mean, you should be able to look at the chart. Remember, if you just look at the chart, you're looking at a some molecule on the chart that can accept or donate electrons. All the molecules above it will give electrons to that molecule, and all the molecules below it will not. And so that's one way of determining it, which is the correct answer. For number 2, it was spontaneous and favorable, unfavorable.
So this one had 2 questions, that 2 answers?
Yep, it also had two answers.
Which one you said was favorable?
The one that is favorable is the one with the negative delta G, and that's NADH donating to, ascorbic acid, actually. So if you look at ascorbic acid, it's kind of like a little bit under, water. O2 rather, whereas NADH is quite a bit above it, so that's favorable. It's gonna donate it, NADH is gonna donate its protons, electrons rather, and nitrate is significantly below it.
Sorry, which compound is the second, answer?
Nitrate, so that's unfavorable.
Okay, and the first one was ascorbic?
They're both ascorbic. The first one was NADH.
N is the number of electrons.
N is the number of electrons.
I felt we're just meant to eyeball it and like kind of like look at the chart and know which one will be more favorable. I know you can do both.
Calculate delta G based on the redox potentials. So, yeah. 21, recently there's been renewed interest in mitochondrial uncoupling agents. This is true, actually. Remember, we talked about dinitrophenol, how it was used briefly as a diet drug until it killed a number of people, and then they withdrew it from the market. That was, in the era actually before the FDA was created. So I wonder what the FDA was doing and why.
Well,
There was a number of instances like that, shall we say.
they passed a bill recently that doesn't allow the FDA and other like government regulators to kind of like oversee anything anymore. It has to go through Congress.
We'll see how that stands up to tests. Yeah, so the whole sort of like creation of blind drug testing, controlled drug testing happened after this was. Also, another notable historical event was they decided they needed to make antibiotics for children that were flavorful, and their first choice to dissolve the flavorings and the antibiotics was polyethylene, not polyethylene glycol, something closely related. Basically, antifreeze. So they dissolved it in antifreeze and killed a number of children and then withdrew it from the market. And shortly afterwards, the FDA was created to oversee the process. But so, way back when, testing drugs on people was a very unregulated thing. Yeah, so 2021, still, mitochondrial uncoupling agents. Remember, an uncoupling agent uncouples the transfer of electrons through the electron chain from the creation of the proton gradient. So dinitrophenol allows protons to pass through the inner membrane.
Sorry, you meant that uncoupling agent as it relates to the mitochondria, not in general.
Yes. It says mitochondrial uncoupling agents, right?
Because it says define uncoupling agent, I didn't know it meant to define it within the context of the mitochondria in particular.
Yeah, that's why the first statement is there, right? So, uncoupling agents, and the danger of imbibing them, since that's what we were talking about in class. So an uncoupling agent uncouples electron transport from ATP production by undermining the proton motive force of the proton gradient. And too much uncoupling, of course, can lead to a lack lack of ATP production in them. The problem with DNF essentially is that what they call a narrow therapeutic window, meaning the difference between effective dosage and deadly is relatively small. So what they're looking for are drugs that will uncouple at a wider dosage range so that you can't easily overdose yourself. And the last one, all the information necessary to answer this question was on the diagram. What I was looking for, though I gave you credit for correct answers that weren't necessarily on the diagram, allosterically inhibits pyruvate dehydrogenase, acetyl-CoA on the diagram. NADH does as well, so if you said that, that's fine. One molecule that activates pyruvate dehydrogenase indirectly. So this is a molecule that activates it indirectly. So CoA inhibits the kinase, so that activates pyruvate dehydrogenase indirectly. Calcium activates the phosphatase, so it's another molecule that activates it indirectly by acting either on the kinase or the phosphatase. And inhibits pyruvate dehydrogenase indirectly, so acetyl-CoA also inhibits the kinase, thus, or activates the kinase, thus inhibiting pyruvate dehydrogenase. Coordinately regulates fructose 1,6 bisphosphate, is just drawn as doing both. Any questions quickly? No, yes.
That's the 18 on the,
No.
we're looking
Oh, it's just urea. I just want you to know the urea cycle.
So you're
Just the very foundation, just the broad outlines of the urea cycle. Where does the ammonia come from? And where does the urea cycle take place and what is it for?
is it on the exam or not?
It will be, but just the simple facts about the urea. I won't ask you about the identity of anything in the urea cycle other than, where the ammonia